All right, let's talk about one of the biggest hurdles in all of calculus, the chain rule. Now, I know it trips up so many people, but here's the thing. It's also the secret engine that powers a lot of modern AI. So today, we're going to crack this thing wide open, figure out how it works, and really understand why it's so incredibly important. Think back to your calculus class for a second. What's that one rule that just always seemed to cause problems? My guess, for a whole lot of you, it's the chain rule. And if that's you, hey, you are not alone. It's a classic stumbling block, and for good reason. And look, that's not just a hunch. It's actually backed by research. A study found that, a significant number of students consistently make the same fundamental mistakes when they try to use it. So if you've ever banged your head against the wall over the chain rule, you're in very good company. But today, we're going to turn that struggle into a strength. Okay, so what is the chain rule even for? Well, at its core, it's about one thing: composite functions. A better way to think about it is a function of a function. You know, like those Russian nesting dolls? You've got an outer function, let's call it F, and then you have an inner function, G, just tucked right inside. The chain rule is the special tool we need to handle these nested situations. So how does this tool actually work? Honestly, it's best to think of it like a simple 4-step recipe. First, you just gotta spot your outer and inner functions. Step 2, you take the derivative of the outer function, kind of ignoring what's on the inside for just a second. Then you find the derivative of that inner function. And for the grand finale, you just multiply those two results together. That's it. That's the whole secret. It's the derivative of the outside times the derivative of the inside. But wait, if it's really just a simple 4-step process, why on earth do so many people get it wrong? Well, that same study we mentioned actually pinpointed the 3 most common places people trip up. So let's walk through them one by one so we know exactly what pitfalls to avoid. The first major trouble spot, you guessed it, trigonometric functions. We're talking sine of 3x or cosine of 3y. This is a classic composite function setup, and it's a place where mistakes are just super, super common. So this slide here really breaks down the 2 main issues. The biggest one, right there in the top row, is just straight up forgetting the chain rule exists. Students will correctly change sine of 3x to cos of 3x, but then they forget to multiply by the derivative of the inside part, which is 3. The other common slip-up in that second row is a simple sign error. It's so easy to forget that the derivative of cosine is negative sine. And here is a perfect example of that second error from a real student's homework. They did the first part right. They differentiated the inner function, 3y, and got 3. That's a great start. But look closely at that sign I've circled. They totally forgot that the derivative of cosine is negative sine. That one tiny little plus sign, it changes the entire answer. Okay, let's move on to our second category of common mistakes. This one involves one of the most famous numbers in all of math, e. With exponential functions, the mistake is almost always the exact same thing. We all remember that the derivative of e to the x is just e to the x. But when that exponent gets a little more complex, like e to the 2x, students often forget that the exponent itself, the 2x, is an inner function. That crucial step is remembering to multiply by the derivative of that exponent. And here it is again, plain as day. The students ask for the derivative of e to the 2x, they write down e to the 2x, and then they just stop. They've completely missed that final critical step of multiplying by 2. This one little omission is probably the most frequent error you see with these exponential functions. All right, finally, we have the third major trouble area, polynomial functions. We're talking about the ones that are raised to a power, or maybe they're stuck under a square root sign. You know, the error here is basically a close cousin to the other two. Students are usually great at applying the power rule to the outside part. They handle the square root just fine, for example, but then they just forget that last step, multiplying by the derivative of the polynomial that's inside the function. Okay, let's look at this last example. So the student is taking the derivative of the square root of 1 minus t, and they absolutely nail the power rule part. They get 1 over 2 times the square root of 1 minus t. Perfect. But what's the derivative of the inside part, the 1 minus t? It's negative 1. And that missing negative sign, circled right there, that is the classic chain rule error caught in the wild. Okay, so we've seen how to do it, and we know what to avoid. But why is it so important to really master this? Well, it turns out this rule is the key to unlocking a super powerful technique called implicit differentiation. This is what we use when we can't easily solve an equation for y, and believe me, it leans heavily on the chain rule. Take a look at this equation right here. I mean, sure, you could probably solve for y, but you'd get this messy square root thing with a plus or minus. It's just not clean. It is so much easier to just leave it as it is and use our new tool. Now, I want you to focus on step 2. This is where all the magic happens. When we take the derivative of that 2y squared term, the power rule gives us 4y. Simple enough. But because y is secretly a function of x, the chain rule kicks in, and it forces us to multiply by the derivative of that inner function, which is dy over dx. That little tag-along term right there, that's the chain rule unlocking the entire problem for us. The rest is just simple algebra. All right, that's a pretty cool math trick. But does any of this actually matter in the real world? Why are we spending all this time mastering a rule about nested functions? Well, the answer is a huge yes, and it's actually at the very heart of some of today's most mind-blowing technology. A research paper on something called tensor calculus puts it very simply. The chain rule is very important for fields like optimization and machine learning. So yeah, this isn't just about passing your next exam, this is about building the future. So how does a math rule from the 1600s end up powering modern AI? Well, it's the engine behind a process called backpropagation, and that's the fundamental way that neural networks learn. Think about it. An AI is just a giant, messy, nested composite function. So when it gets an answer wrong, the chain rule is what allows it to efficiently work its way backward through all those nested layers and calculate exactly how much it needs to tweak each of its millions of parameters to get better. It's literally the foundational logic inside tools like TensorFlow that are driving the entire AI revolution. So let's end on this idea. When you strip it all down, the chain rule is just a way of describing how a small change in one little part of a nested system can ripple outwards and affect the whole thing. And when you think about it like that, you start to see it everywhere. What other complex systems, from biology to economics, work on this exact same principle? The chain rule isn't just some formula to memorize for a test, it's a powerful model for understanding our deeply interconnected world.